One of the reasons why is that it tends to be a more chronic issue where people are driving into flooded roads at night. And it's usually guys about my age that tend to do this. And so that's the demographic. But we drive into flooded roads at night and you become buoyant. And if there's a current, you get carried away. And that's the greatest danger in flooding. We don't tend to hear a lot about flooding fatalities because you might only lose one or two people at a time. And although losing anybody is too many, oftentimes we'll hear more about tornadoes just similar to what just happened this past weekend on Friday and Saturday. We lost 40 or over 40 people from tornadoes. When a strong or violent tornado hits a population center, we tend to lose more people, and it's a more of a news story. And so a lot of times the perception is tornadoes lead the way, when in fact it's flooding that is taking more lives than anything else. And I'll say this too: if you're here in Kansas, it's driving in bad weather that is number one. We lose 10 times as many people, 15 times as many people to driving in bad weather every year. And that includes ice and snow, rain, and unfortunately, just like we saw last Friday, it can be blowing dust. Any sort of a situation like that. And we had the terrible pileup out west near Goodland, and we lost, I believe it was at least 8 people in that pileup as well. So driving in bad weather is the greater risk to you. So wear your seatbelt, slow down, pay attention is the lesson there. Here's the mortality stats from and this only goes up through last year, does not include this year. But one of the things that stands out is the red to our south and east, and especially across Kentucky, Tennessee, Alabama, Mississippi. And a lot of people ask, is Tornado Alley shifting away from Kansas? And the answer is no, it's not. If anything, maybe more appropriate to say an expansion to the south and east. Tornadoes are not moving away from Kansas. But one of the things also that leads to the higher mortality down to the southeast is that the population density is higher in that part of the country. And more of those people live in manufactured homes, mobile homes. And also, the third uh, point to make about the mortality in tornadoes in that part of the country is that more of their tornadoes occur at night. And it's not just after dark before you go to bed, it's after midnight. More of their tornadoes happen at night, including late at night. And that's different than Kansas. We tend to see most of our tornadoes before midnight, before we go to bed. And then afterwards, they drop off considerably. And so there's a lot more vulnerability and risk from tornadoes down to the southeast from those factors than we tend to see here in Kansas. Nationally, this is over the last, what is it, 33 years or so, the number of mortality or fatalities from tornadoes in 2011 stands out. It's a huge, huge anomaly. And that's when we had violent tornadoes hitting big cities. That was Joplin, that was Tuscaloosa, that was big tornadoes hitting Alabama, Mississippi, and then, like I said, Joplin as well. And we lost a lot of people in those big tornadoes, violent tornadoes hitting population centers. The numbers of tornadoes across the state, it's interesting to see them, sort of the trends over the years. The highest year was 2008. The lowest year was, oddly enough, was 2020, the same year as the pandemic came out. So I don't know how to explain that. We had a lot of chasers out. I remember that. I know they were out there looking for tornadoes. So I don't know what happened there. I don't know how to explain that. The lowest on record number of tornadoes documented, but it was 2020. Now, relatively speaking, over the last 10 years, we've had more years below average than above. But that doesn't mean that we can get complacent, certainly, because we still, if we look at the 30-year averages, we're up there. Tornado Alley is not shifting away from Kansas. It's not shifting away from the Central Plains. We're still in it. And so we still need to be very aware of the risks associated with strong or violent tornadoes, because they do pose the greatest risk for a mass casualty event here in the state. Peak months, we're leading up to it. No surprises here. Historically, we've seen most tornadoes in April, May, and June. The worst tornadoes historically in May and June. Those are the 2 months for the strongest tornadoes in the state of Kansas. The time of the day, this one is local time. So basically 12 is noon, 16 is 4 p.m., 18 is 6 p.m., 0 is midnight, And so you see how it peaks around 5 or 6 in the evening, and then it really falls off after midnight. And that's good because that tends to help us in terms of our situational awareness. We're awake, we're not sleeping when tornadoes are most likely to occur here in Kansas. When we talk about sheltering options, this is very important. We talk about it every year, but we see it, and we see it again in what happened just this past weekend down to our southeast. Um, Underground storm shelter or an engineered storm or safe room above ground. Number one options: get as low as you can and put as many walls between you and the outside as possible. That's the general principle. You follow that general principle, you're going to survive even the strong and the violent tornadoes. But you've got to do that. If you don't have a basement, lowest floor, an interior room or closet, stay away from windows. The top picture that you see here, right up in here, this is an exterior wall that has exposed what was a small uh, bathroom. And oftentimes, when we look at homes that are destroyed by tornadoes or damaged by tornadoes, the roof is what goes first. Homes fail from the top down. And by that, I mean the roof um, is removed, and usually it's the wind gets in through maybe an overhead garage door or something like that. And when the wind gets in, it's going to find a way out. And usually it punches out an opposing wall, and then it begins to lift the roof off. And when you lift the roof off, the support for the walls tends to go. So your exterior walls then go. And so with that in mind, it's the smaller interior rooms on the lowest floor that tend to be the better options for sheltering with a tornado. But you want to cover up with something heavy or get underneath something sturdy if you can, because it's all this debris that you see in the bottom picture that is blowing around at 150 miles an hour, 180 miles an hour. That's the greatest danger in a tornado. And then plan ahead. We talk so much about the vulnerability of those that live in manufactured homes, and they have to get out. They cannot stay where they're at if they're in the path of a strong or a violent tornado, because it is an extremely dangerous thing to do. Cover your neck and head. I mentioned this before about getting underneath something sturdy, covering up with something heavy. Back in 2011, many of the fatalities and serious injuries were due to blunt force trauma to the head. And so a lot of the medical folks across the country started talking about the importance of helmets in a tornado, in a worst case scenario, being better than nothing at all to protect yourself. And then when I say helmets, it's not necessarily the $500 motorcycle helmet. It can be just a bike helmet that provides protection over and above nothing at all. Now, when I was growing up, it seemed like the story would always be that when we heard about tornadoes, it was a tornado hits a mobile home park, and so you grew up wondering if tornadoes were attracted to mobile homes, and they're not. But the idea of that was that when we heard about tornadoes, it was usually because somebody had lost their life from a tornado, and it was usually due to them living in a mobile home or a manufactured home. And that statistic back then is still true today, and that the majority of our tornado fatalities continue to occur in manufactured homes, even though it's only a small percentage of the entire housing stock. We're still seeing most of the fatalities occur in those settings, and we have to talk about why that is and what you can do to keep yourself safer. And it's really for manufactured residents, from experts and survivors, is clear. You have to go somewhere else. If you have a community shelter, that's great. If you don't, then you have to think about, where are you going to go? Where's the nearest? If you've got a friend or a neighbor that has maybe a safe room, or they have a basement, they have a better shelter option than you do, then that should be something that you think about and ask them and reach out to them and ask if that's something that you could do as well, and share in that shelter. Um, it's an extremely dangerous place to be. And the reason is that mobile homes, unlike traditional homes, they fail from the bottom up, which is to say that mobile homes are anchored to the ground in some form or fashion, or they should be. But that anchoring only withstands forces up to about 130, 35 miles an hour before they fail. And those homes then are airborne, or worse, they just disintegrate. And so, in other words, when we go out and do damage surveys, there is no EF3 damage that specifically addresses the degree of damage to a mobile home. Mobile homes are destroyed by the time you get to higher end EF2 damage. And this is what we're looking at here in Alabama. Winds estimated to about 135 miles an hour. Now, the vast majority of the fatalities in this tornado occurred in manufactured homes. And in all of those cases, they were either improperly anchored or they were not anchored at all. And you would be surprised how many times when we go out and do damage surveys and we look at manufactured homes, how many of them are not anchored at all. They're just sitting on cinder blocks. And that's just incredibly dangerous. It doesn't take a strong tornado to blow a manufactured home off cinder blocks when there's no anchoring. It can be a 75-mile-an-hour wind. And so this is a challenge that we face with more people living in manufactured homes, is to, number one, properly anchor it, and number two, convince people that they have to have an alternative shelter location outside of their manufactured home, because it is dangerous. And it continues to be extremely dangerous. Preparedness means putting together a plan and then practicing the plan, then having multiple ways to receive warning information, situational awareness. We talk about a plan. If you live in a manufactured home, the plan needs to be to go to the community shelter if you have one, or to a friend or a neighbor's house that has a better sheltering option. So no matter where you're at home, work, school, where's the tornado shelter? How long will it take to get there? And have some sort of a kit ready to go that includes maybe a bike helmet, closed-toed shoes, whistles, battery backups for things like phones, light. I talk a lot about safety kits. And here in Kansas, the most likely thing, the probability of being hit by a strong or violent tornado is relatively low. You're more likely to lose power for an extended period of time from something like an ice storm. And so it's always a good idea to put together something that helps you better prepare for an extended power outage, like a battery, having batteries ready to go, battery powered flashlights, radios, and so some sort of a battery backup or battery pack for mobile devices that can store energy and have to recharge your mobile devices if you are out of power for an extended period of time. The other thing with tornadoes that we talk about, closed-toed shoes. If you've ever been through a tornado, you understand the amount of debris that's strewn about. It can be glass, everything, you name it. And so the importance of having shoes on when you're going through something like that is also very important as well. Just being prepared, having that ready to go, and then practicing the plan. Evacuating if you live in a mobile home and going somewhere else should be part of the plan. That's very, very important. Situational awareness is a crucial component to this too, because if the warning's out or the tornado watch comes out, but you don't receive it, it's not doing you any good. And so having the ability to receive this information and have a couple of different ways to do it in case the power goes out, and you have something like a battery powered radio or your mobile device to give you that information no matter where you're at or if you have power or not. That's important as well. I'm old enough to remember when local TV, commercial TV and radio were really the standards for the foundation of disseminating important emergency information. And I still think that's the case today, even though we've become so fragmented through the media, where people are looking at streaming services and things like that, or they're listening to podcasts on their mobile device, whatever it might be. I still think when we get that alert on your mobile device through wireless emergency alerts, or you hear the siren going off maybe outside, that's an alert to stop what you're doing, go find out additional information through your local media partners. And I think that's still one of the most powerful ways to quickly get the information you need to personalize and verify what's going on so that you can take action to protect yourself as well in this day and age. I hope all of you out there listening have a source of radar information on your phone. There are a lot of things out there these days that can provide information for you, including your location with respect to the storms. I think this is a screenshot from a program called Radar Scope, which is an excellent app that's out there that can provide that information for you for your situational awareness. A lot of just general weather apps out there for forecast information and deliver alerts to you as well. It doesn't matter to me, whatever one you want to pick. It just needs to be one that you find that works for you. It can be any of these. There are free warning apps that are out there too. There's one from the Red Cross, and there's a lot of them out there. If you just do a search for weather apps or weather warning apps, there's tremendous amount of choices out there. Some things on social media on X that used to be Twitter, some feeds, tornado warning feeds, and things like that that'll give you that information as well based on where you're at with respect to the specific office that you may be relying on. Here's a screenshot of one of those programs called Radar Scope. What you are looking at is the radar reflectivity image right here over Bangor and Sparta, Wisconsin. This is me. I'm in Tomah, Wisconsin, and you see the radar reflectivity with respect to my position. And you also see the Weather Service warnings here. The red box is the tornado warning. You click on that red box, it gives you the text of that warning. The yellow boxes are severe thunderstorm warnings. This is fantastic information to have and have with you no matter where you're at, because it gives you the information you need to stay away from these thunderstorms, because certainly that's what I would rather do. I don't want to get too close to this supercell because it's probably producing tennis ball sized hail, and get away from that, or obviously the tornadoes. So this is an example of the wireless emergency alert sound and text that you would see if you were in a tornado warning. This is a program, it's an opt-out program that is managed by FEMA, but the Weather Service participates in the program, and we send you certain warning information, and I'll tell you what that is here in a second. Most of you have heard that noise. If you live here in Kansas, you might have been in a tornado warning and received that, but most people receive that when they get an Amber Alert on their phone. So it's the same program, just different information. Amber Alerts are coming from KBI or state law enforcement agencies. The weather information is coming from the National Weather Service. It's just an alert to get your attention, stop what you're doing, and go and find out additional information from your local media. What will you receive through wireless emergency alerts on your phone? A tornado warning. If you're in or very near that polygon, you'll receive that alert. If you are in a serious flash flood warning, it's a threat to life and property, you will receive that alert. And also, we started about 4 years ago. We're also now delivering what I'll call higher end severe thunderstorm warnings. And those are severe thunderstorm warnings that include 80-mile-an-hour winds and or baseball sized hail or larger. And that will also trigger your phone. And there's also other things that will trigger your phone, like dust storm warnings, snow squall warnings, things that are less common across parts of Northeast Kansas anyway than other parts of the country. But those will also trigger the wireless emergency alerts program as well. It's an opt-out program, meaning it's on any phone that you've purchased in the last 5 years. It's on that phone. You can turn it off if you want, but I leave mine on because I just don't get that many of them. This is an example of weather radio. Weather radio has been around, I think, longer than I've been alive. And it's not to say that it's not worthwhile. It is. It still fills a void in rural areas where the cell signal is potentially too weak to deliver a reliable cell service to you wherever you're at. This is an FM. These are networks of FM radio or wavelength frequencies. Now, they're a little different than your favorite FM commercial radio station because these are more like 300 or 1,000 watt transmitters. Your favorite commercial radio station might be 50,000 or 100,000 watts. So these are lower power. And so the distance that they carry is limited. And also because they operate on this wavelength, they also are impacted by terrain factors. So you may live in a valley, and that may affect the ability to receive the signal. So there's things that can degrade the signal strength at your various location wherever you're at, but it still does fill a void in certain areas where cell signals aren't that great. And there's plenty of those spots. If you've ever been to parts of rural Kansas and even Wabunsee County, just west of Topeka, the cell signal's not all that great in spots. So this still plays a role. Other information that can help you stay aware in the days in advance of severe weather. Maybe some of you were doing this already last week on Wednesday and Thursday. There's information that can provide just general awareness about the areas at risk for severe weather. And one of those, and I'll talk about that, is the Storm Prediction Center. They do a really good job of drawing areas where they believe there's a risk for severe storms within 25 miles of a point. And based off the probability of severe weather occurring within 25 miles of a point, they'll use words and colors to try to convey that risk. And it goes from a marginal, slight, enhanced, moderate, high, based on increasing probabilities for bad things to happen. It can be hail, it can be wind, it can be tornadoes, and based on those various factors, the meteorologist at the Storm Prediction Center will draw outlook areas for today right through day 7. So they'll not only do it for today and tomorrow and the day after tomorrow, but all the way for the next week. And so this can be a very, very useful resource as well. If you're interested, if you've never looked at it before, just Google or whatever search is your favorite source of search, just Storm Prediction Center, and it'll take you to their website. They do a really good job of outlining the areas at risk for severe storms. Then your local forecast office, your local National Weather Service offices that are staffed 24 hours a day, 365 days a year, 7 days a week. We're here. And what we do, and our job is to do the best we can to distill down the details locally for the what, where, and when. We try to answer questions of what's going to happen, where is the greatest risk, and when. And we do that in a PDF document. It has various names, but if there's something going on, you'll find it at the top right of our homepage. And in this case, this was last Thursday, I believe it was, when we had the risk for severe storms and wildfire danger as well. This is what that document looked like: what, where, when, actions, and then the key messages for the severe weather. Thankfully, the severe weather stayed just toward northeast, but this is the way it looked back on the 13th of March during the afternoon hours. And so this is the information you get from your local weather service offices. We take the Storm Prediction Center's information and then we try to tailor it to the specific area that you live in here. Okay, enough of the preparedness and awareness stuff. Let's talk about these storms that we deal with. And we'll talk a lot about supercells. What you see there, and I hope the video, this is an animated GIF, so I hope it's translating well, and it shows you that rotating updraft called a mesocyclone. Mike Hollinshead, thank you very much for letting us use your creations here. This is an example of a rotating updraft called a mesocyclone of a thunderstorm that we call supercell. And we'll talk more about why they rotate and what that means for these storms here in a second as well. So real fast, and I don't want to bore you, but we got to talk about this because this time of the year, it's especially important for Kansas because in March, especially in early spring, we lack the sufficient moisture to get severe weather and certainly tornadoes specifically. But we need moisture, a source of moisture in the lowest 6,000 feet of the atmosphere. And then we need something called buoyancy or instability. And then we need some form of lift in the atmosphere. We need something to mechanically lift the atmosphere or through heating as well as another way to lift the atmosphere. Our source of moisture. So if you're curious, if you live in Kansas and you're wondering what is the lower threshold for typical severe weather cases for tornadoes in Kansas, and it's really low to mid 50 dew points. Here in Northeast Kansas, we really are looking at a threshold of, we need at least low to mid 50 dew points to get tornadoes. If you have dew points lower than that, the cloud bases tend to be too high. The processes in these thunderstorms, such as downdrafts, tend to be too cold and too deep, and it tends to disrupt the low-level circulation. It's just harder to get tornadoes when the atmosphere is drier. And so you really look for dew points coming out of the Gulf of whatever it's called these days of at least in the 50s, 55, mid to 50s or higher for tornado setups here in the state of Kansas. And the moisture source is the Gulf of Mexico. And the other ingredient that we need is buoyancy, instability, which is the idea that you have warmer air near the surface of the ground or lower atmosphere, and you have cooler air aloft. When you have warmer air beneath cooler air, it's considered unstable. And that warmer air will start to rise and it will continue to rise until it hits an equilibrium layer high up in the atmosphere. But around here, because of our geography, we often tend to have a layer of warmer air that acts like a lid on the atmosphere. So around noon, the sun is heating the ground heats the air nearest to it, and the air starts to rise. It may rise sufficiently to create a cloud, but that cloud, it actually hits that layer of warmer air that is originated somewhere over New Mexico, the higher plateau of New Mexico or Colorado, and that acts like a lid on the atmosphere. But the heating continues into maybe late afternoon, and at some point, either the heating of the air is sufficient by itself, or more likely, it is the heating of the air plus another factor, which is lift from a front that will be sufficient to cause thunderstorms to form. And around here in eastern Kansas and in central Kansas, oftentimes our severe weather setups are driven by dry lines. And dry lines are boundaries that separate drier air from the west with southwesterly winds from more moist air to the east. And that'll be carried on southeast or southerly winds. And it causes a line of convergence to form. And along that line, we get lift. And in some cases, it's sufficient to create an explosive development of storms. And that's what we see here. This is a visible satellite loop. And so what you're seeing is the sun's reflected energy, or yeah, it's just the reflected light of the sun off the top of the clouds. And we use this a lot in severe weather to look for boundaries like dry lines, or look for areas where we see thunderstorms beginning to develop or trying to develop. And then oftentimes we'll try to convey that information an hour or so before the storms develop in some graphics, and we'll put that out to our partners in the social media, and then also our partners in emergency management through what we call chat software as well. So that's a great example of thunderstorms exploding along a boundary. Now, thunderstorms are alive. They breathe. When they are born, they breathe what's primarily inflow and updraft. And they reach a mature stage. They start to create rain or hail that cools the air, and it drags it down, and it evaporates and causes more cooling, and it causes a downdraft. And we're going to talk mostly about this middle picture here, the mature stage of thunderstorms, especially supercell thunderstorms, because that's when we see the important features that might lead to certain things like tornadoes. But all thunderstorms, including supercells, eventually run out of a favorable environment and die off, sink, evaporate, and disappear. And so we're going to really focus in on this mature stage for supercell thunderstorms. When I talk to people about thunderstorms, specifically supercells, I tell them again that they are alive. They breathe. They inhale warm, humid air. And that warm, humid air that they breathe in is called inflow and updraft. And it often occurs as viewed looking to the west, off to the left here, where we have a rain-free base and then the updraft. Where they exhale cold, moist air, we call that downdraft and outflow. And we see that in the form of the rain area off to the right here. And the reason that it's off to the right, we're going to get to that in a second, as viewed from the east looking west, is because of something called wind shear. And we're going to get to that here in a second. But my point is, in bringing that up, is perspective. Your perspective with respect to these storms is very important to seeing these features with respect to one another, the updraft being to the left and the downdraft to the right, and then understanding what it is that you're looking at. You're understanding that, all right, we have the lower in here. This is the updraft where the air is going in. We have the downdraft over here with this thunderstorm. Understanding the processes that are going on in that thunderstorm to help you better understand what may happen in the future in those certain parts of those thunderstorms. Tonight, I'm going to talk primarily about lines of storms. The process of downdraft and outflow dominates, forms a very a cold pool of air or a cold pool of air that's very large tends to accelerate out ahead of the storm or away from the thunderstorm. It looks different. The cloud features that are dominant in lines of storms look different, and they also tend to look different on radar. Radar reflectivity with a line of storms looks very different than it does from a supercell that's off on its own. We see that in the bottom right. These are both reflectivity images for a line of storms and a bow echo that tends to look like that, where the bow area is representing where the wind is accelerating out and pushing out ahead of the rest of the line, and that's where you tend to get the strongest winds. Meanwhile, the supercell we see here has that funny shape to it called the hook echo. And that represents the process of rotation in this part of the thunderstorm. And we'll get to that here in a second. They look different when you're seeing the cloud features, and they also look different when you're looking at them on radar. They look different. They represent different processes that are going on. Lines of storms first, pretty self-explanatory here. Line of storms that forms into a line that has a large pool of cold air behind it that tends to drive its motion. And it also forms this feature right here that you see that's the leading edge of that gust front or cold pool of air called a shelf cloud. And so that's what's most common and seen in these lines of storms. The process of downdraft and outflow dominate, form this shelf cloud along the leading edge of the cold pool of air. Also, the shapes to these reflectivity signatures mean, or they can mean something. They can be important. When it comes to the lines of storms, if you see small areas that have bows, like you see here, that can represent a localized area of stronger winds, where you have maybe 70, 80-mile-an-hour winds in this little area that's bowing out ahead of maybe the rest of the line. And so you want to look for those things in lines of storms. Look for the shape of that, in addition to the fact that you're just looking at a line itself. Here's a video that I hope translates pretty well. That shows us looking at a line of storms approaching. We see the tops, the anvil clouds, and then off to the closer to us, we see the new updrafts going up off to the right, right up here. It looks like a big old fist of cauliflower. Now, just above the tree line, we start to see the leading edge of the cold pool of air forced by a downdraft and outflow. If you see this feature, it's called the shelf cloud. Get ready for strong straight line winds. Force is first, and then comes the rain. That's a classic scenario or a progression of features that you would see with a line of storms as it moves over your area. Here are some other examples of that feature called a shelf cloud. It occurs along the leading edge of the cold pool of air that's formed by downdraft and outflow. It tends to drive these features. And if you see that, think downdraft outflow. Think process of downdraft and outflow is dominating in this region of the thunderstorm. This was what we call a high precipitation supercell looking north out of Chase County. Chase County is where, at the time, the Symphony on the Prairie, it's a big to-do. Lots of thousands of people out in the middle of nowhere, and we had a big supercell thunderstorm approaching. That supercell had become what they call outflow dominant by this time. And so that meant that the tornado threat was lowering or decreasing, but the wind threat was increasing. And it was forming into a very large shelf cloud that you can see here. So it delineates that area where we had downdraft and outflow approaching our area, a very large, long, narrow cloud produced by the gust front. Here's another example of a shelf cloud, a little more subtle in this case, but again, the most characteristic detail of this is the very long nature to this cloud. It is the leading edge of a cold pool of air that is pushing out away from the storm. And oftentimes you can get scary looking clouds along the leading edge of the storm, little fingers that form, look like funnels. They're not funnels, they're just SLCs, scary looking clouds that can form along the leading edge. And you see one of those right there. See that right there? That's not a funnel, that's an SLC. And then you see these clouds back here. These are scud clouds. We call them stratocumulus under deck. Scud clouds. They are scary looking clouds. And sometimes people will see those and think that that could be a funnel or a tornado, and it's not. They are clouds that got trapped in the cooler area of air behind the shelf, cooler, more moist air. And sometimes that gets tugged upwards and forms a cloud down a little bit lower than the rest of the cloud base. Those are not associated with tornadoes. Now, there are features associated with this type of storm that can be associated with inflow and updraft and also with the development of a tornado. Supercell thunderstorms are unique. This is what makes them unique. It is their rotating updraft called a mesocyclone. That what is really what makes them special compared to other thunderstorms. It allows them to live longer and also to be stronger. The updraft, as it rotates, actually causes accelerations upward and allows these storms to be stronger than other types of thunderstorms. Supercells are prolific hail producers. Chances are a supercell in a classic environment like this with energy is probably going to produce at least golf ball sized hail, if not larger. Now, in the right environment, the right low level environment, and when I say that, I mean the lowest few thousand feet, they can produce the strong and the violent tornadoes. In fact, any strong or violent tornado that you have ever heard of is likely has been associated or spawned by a supercell. However, research over the last 30 years has told us that the majority of these never do produce tornadoes. It has to be the right ingredients that come together in the lowest few thousand feet that are important to get a storm like this to produce a tornado. And we'll talk a little bit about what the characteristics in the clouds might be to show you that you're dealing with one of those minority that may produce a tornado versus the others that don't. And then these also can produce damaging winds and flash flooding as well. So what causes these storms to rotate? Number one, let's just pretend we're out in what we call the Flint Hills of Kansas. We're looking to the west and we see the base of one of these supercell thunderstorms. This was probably would be considered or classified a low precipitation supercell because there's not a lot of rain back here off to the right. But the reason they rotate is wind shear. Wind shear is just a way to explain that the winds get stronger as you go up in the atmosphere. And that causes horizontal tubes of spin to develop that get tilted up into the vertical. And that causes these storms to rotate. And that actually causes the storm to have a separate updraft and downdraft area. So the rain and hail tends to fall downwind of the updraft area, as seen from the east looking west. We see our rain and hail over here, not falling back through the updraft. And that allows these storms to live longer and be stronger than they otherwise would be. We also get directional shear. So not only do the winds get stronger as you head up in the atmosphere, but they also change directions. So before a severe weather event in Kansas, we probably have winds out of the south or southeast to 20 to 30 miles an hour, bringing Gulf moisture northward in the form of dew points in the 60s. But then aloft, maybe at 8,000 feet, we've got southwesterly winds at 70 miles an hour, bringing dry, warm air from the elevated plateau of New Mexico. And that acts like a cap on the atmosphere. But then aloft above that, we've got even stronger winds out of the west-southwest. That actually causes horizontal tubes of spin that get tilted into the vertical, and that's what helps these storms attain rotation. Their updrafts attain rotation. Now, specifically, how do tornadoes form? Where do the tornadoes get there? What's their source of spin? Well, part of their source of spin is actually over here. There's a boundary that forms over here where we have rain-cooled air separating that from the warm inflow air here. And believe it or not, there's spin that gets ingested into this part of the storm right here. And that's the spin that tends to get tilted into the vertical to produce a tornado. Now, a backyard experiment, when you've got no wind shear, the air at the jet stream level is 30 miles an hour. In the summertime here in Kansas, the jet stream goes into northern US or Canada. The winds aloft are about the same speed as they are at the ground. So when we get an updraft, it collapses back down on itself pretty quick. And so any storms tend not to last very long. They're not organized, but they can produce downdrafts. And some of those could be damaging downdrafts. We call them downbursts or microbursts. That can happen. We're not going to talk about that tonight. But when you add wind shear into the mix, this is what happens. The wind and the hail goes up and it gets dumped downwind. We're looking at the storm towards the west, and all that jet stream energy is blowing the wind and the hail, or the rain and the hail, off to the right here. And so the updraft and the downdraft are separate. In nature, this is what it looks like. This is not our little backyard experiment, but we've got inflow and updraft going up into this sort of rounded updraft feature that you see here. And then our rain and our hail is being dumped over here, downwind, because of wind shear. And so they are separate, and we get that organization. You say, hang on a second, Chad, wait a minute, look at that, I see rain back here, there's a rain shaft back here. Yeah, there is. Some of that rain and hail gets pulled back behind this rotating, remember this thing is rotating counterclockwise, and some of that rain and hail gets pulled back this way and down and into the base of the backside of the updraft. That's what you and I see as the radar indicated hook echo. This is an example of that. We are in Greenwood County, Kansas, down in east central, southeast Kansas. We're looking to the west, and we see the rotating updraft of a supercell thunderstorm. Now, we also are using our radar app to show us our location with respect to the storm. We're looking to the northwest. What do we see? Well, when we look at the cloud feature, we see this thing right here, the rotating updraft. That rotating updraft is out here in front of the reflectivity signature that you see right here on your radar app. The radar reflectivity that you see is depicting the rain and the hail that's falling out of that thunderstorm at some level that you're looking at here on radar, which is probably 3,000 to 4,000 feet above the ground. That's what you're looking at right here. It's the stuff that's falling out. That's this stuff right here that is north and just east of this rotating updraft. You don't see the rotating updraft on radar. Radar reflectivity is not going to show you this thing right here. You'll see the rain and the hail further up, way up high, but you're not looking at that when you're looking at a radar app. You're looking at usually the half degree, which is the lowest level, and you tend to see this stuff right here. Now, this rain shaft area right here, guess what that is? That's what makes up this little area right here, this little appendage area. It can look more like a hook sometimes, but that's what you see when you're a spotter in the field. You see that rain shaft area, and that's depicting where some of this rain and hail is getting wrapped back behind that updraft. You see that as an appendage or a hook on radar, but you see that as a rain shaft here. If this is going to produce a tornado, it's going to be in what we call the action area. The action area tends to be where you have the updraft and the downdraft. It's in between that area. We're looking to the west, remember, and it's in this area. We see somewhat of a sort of a weak lowering here, and that's your wall cloud. And so we're going to watch that area. It serves as a landmark. Watch for signs of organized persistent rotation about a vertical axis in that area. Here's another example. We're looking west-southwest in this case. Here's our spaceship rotating mesocyclone, the updraft tower, the rain and hail being dumped downwind off to the right. That is what we call a rain-free base. And you say, Chad, look at all that rain back behind there. Yep, there is. And that's because you and I are here. We're looking to the west. And you see this right here on radar reflectivity. You see all this stuff right here. All that rain and hail is also being tugged back around the updraft and down into the base, the backside of that updraft. And it forms that hook shape that you see there. That hook shape that you see in reflectivity is representing the process of rotation in the thunderstorm. It doesn't mean there's a tornado, but it tells you that the process of rotation is occurring, counterclockwise rotation. This cloud feature that you see is out ahead of it. It's over here. That's what we're looking at. Our lowering in the action area is here. We're looking for that wall cloud, looking for signs of organized persistent rotation. When you see organized persistent rotation in the low levels, it tells you that you're dealing with an atmosphere that can support tornadoes. That's the key to look for, is signs of low-level rotation in these thunderstorms. That tells you that you're dealing with an environment that's capable of supporting tornadoes as well. Looking down and talking a little bit more about sort of a top-down view, the cloud feature that I've been showing you is that white area out in front that's rotating. That's the mesocyclone. If you want to be a smart chaser, smart spotter, you want to be in this area, what we call the inflow area. You don't want to be up here. This is too dangerous. You don't want to be up there, especially if you're just starting and learning about storms. It's a dangerous area because these tend to move east northeast, puts you in the path of the tornado. You want to be east here if you can, with an escape route to the south or east, a paved road if it's available, because these can become muddy and flooded. And so you want an escape route, but it offers you the best vantage point into the important features in the thunderstorm. With radar reflectivity, the colors represent the stuff in the storm. And usually the stuff in the storm is rain or hail. And the colors indicate the intensity of the rain or maybe the presence of hail. And the shapes represent the processes going on. I mentioned that before. That hook shape represents the process of counterclockwise rotation. The low rain, if there is one, is going to be right in about here in the action area. You're going to feel a warm, maybe humid air at your back as you face the storm. And that's that storm inhaling warm, humid air, especially if it starts to get stronger. That's an important thing to make note of because it may be getting more intensifying. I mentioned before, there's a boundary over here. We call it a forward flank boundary. And this creates a source of low-level spin that can be sucked into this part of the storm and then get tilted into the vertical and produce a tornado. So that's kind of an area that we watch too on radar for signs of potential tornadoes. And then there's also, and tonight I'm not going to get into this too much, but there's also another process that leads to tornado formations in supercells. And sometimes you'll see it as a brighter area off to the left of the lowering and the developing tornado. It's a brighter area that tends to form is a sort of a waterfall of air, descends, warms, evaporates clouds, and then helps to tilt some of the spin into the vertical. Call it a rear flank downdraft. But all this kind of comes together in what we call the action area. And you would like to be in here, not too close, but in this area, because it offers you the best vantage point for the important low-level features in the updraft and inflow region of the supercell thunderstorm. And one of those features is called the wall cloud. And we see it there. Now, wall clouds are a little bit overrated in the sense that when people see them, they tend to believe that that means that this thing's going to produce a tornado. That's not the case. What you want to look for is if you see a lowering, you've identified the strongest part of the updraft, watch that area, use it as a landmark to focus your attention on. Now, look for signs of organized persistent rotation about a vertical axis. Watch it. And that's the important point to note about wall clouds. You've seen something important. Now watch it for signs of organized persistent rotation. As viewed from the east looking towards the west, sometimes you'll see the wall cloud slope down towards the rain area, sometimes. And that's because some of this rain-cooled air gets tugged back up into it. Think of this as a vacuum cleaner underneath the strongest part of the updraft, and it'll suck some of this and tug some of this rain-cooled air up into the area, and it tends to form a tail down lower towards the rain-cooled area. Here's an example of that. This will play in, hopefully, in motion for you. We're looking to the west-northwest, the underside of a rotating thunderstorm called a supercell. And underneath it, we do see rotation. We see in the foreground, we see clouds moving left to right, and the background right to left. And you see here a bit of a tail growing. This is an example of one of those tail clouds as it's pulling rain-cooled air into it. Upward motion into this area. Uh-oh, look at this. It's a brighter area off to the left. As some of that descending air called the rear flank downdraft starts to cut into this part of the circulation, and it almost forms, we call it a cut, a rear flank downdraft cut, brighter area. It tries to tighten up the circulation. And holy cow, it's trying. And it's trying, but as a spotter, I don't see anything at this point. Aside from the RFD cut into the base of the circulation, I don't see any sort of a funnel. I don't see a tornado. I don't see any debris at the ground. But man, it's trying. So nothing so far. Maybe, you have a lowering here. This is an area we're watching still close. But in this case, you know what? It looks like it failed. But guess what? You got to follow this area because it's going to cycle. It's going to try and do it again in maybe another 20 minutes or so. Supercell storms live sometimes 10 to 12 hours, and they may do this every 20 minutes or so. And they'll try a new RFD, will cut into it, and they may move into an environment that has stronger wind shear, better moisture, whatever it might be, and it'll start to produce tornadoes where it failed the first few times. So that's an example of the low level circulation underneath one of these supercells trying to produce a tornado. We are looking to the west northwest, and here's an obvious lowering here. The rain and hail is over here to the left. See these smooth clouds here over here? These are inflow bands. I don't want to get too complicated tonight, but sometimes you'll see this in this part of the thunderstorm, where it's again breathing warm, humid air. It's sort of inhaling this into the updraft, the rotating updraft that we see here. And you'll see these smooth areas along the leading edge between the forward flank downdraft rain area off to the right and the rest of the area. All right, here's a great example. I mentioned before dew points. If we have dew points in the 50s, we tend to see maybe low precipitation supercells or more classic supercells. Dew points in the 60s, classic supercells. If we get higher amounts of moisture in the atmosphere, dew points maybe in the 70s, low 70s, well, we get what we call high precipitation supercells. And there's a lot more rain that ends up wrapping around the circulation of these supercells, and it makes it harder to see the important features in the storm. Not only do they look different on reflectivity, instead of the classic hook, you may have a kidney bean-like appearance, if you even get that at all. Sometimes they just look like a blob. But in this case, you may get an inflow notch on the east side, looks like a kidney bean, but you lose contrast. Here's the rain-free base of the updraft. Here's our lowering right here. And even if you're lucky enough to see something like this, if an HP produces a tornado, oftentimes it'll get sucked back into the rain area, and it'll be completely obscured by rain. It'll be invisible to the naked eye. HPs are very, very dangerous to try to spot, because if it is producing a tornado, it may be invisible to you. Here's another example of a more classic case. We're looking to the west. Here's a lowering. Here's our rain-free base, the base of where the air is going up into the thunderstorm. Up here, we see the updraft, the sort of the updraft that looks like a fist of cauliflower punching up into the atmosphere. And then below that, we have our lowering. And so we're going to get closer to this and look for signs of organized persistent rotation about a vertical axis. And then off to the right, we see the forward flank precipitation off to the right as well. I use the word lowering again and again and again. Now, if you get closer to this feature, it may stop looking like a lowering, and it may just look like a sort of a rounded base or a bowl shape underneath of the base of the updraft. And sometimes the features lose our perspective, or our depth perception changes. And so instead of a lowering, it just looks like a swirling cloud base when you get closer to it. And you just want to stay a safe distance away. This is the development of a strong and what was to become a violent tornado in parts of central Kansas back in May of 2016. And you can kind of see it here. This is the lowering as it started to develop. This is literally the beginning of that tornado. And sometimes that happens. Now, this is an example of a rotating wall cloud, or a rotating cloud base, really underneath it, underneath the rounded updraft base. And this turned into just a large tornado. It went from sort of this shape to sort of an elephant trunk to a wedge tornado in about 15, 20 minutes. In this case at all. Didn't take much time at all. Funnel clouds. Traditional funnel clouds are obvious. They look like this. They don't visibly have a circulation or a debris circulation at the ground, because if they do, then it is a tornado. In this case, we just maybe are too far away to see if there's any debris at the ground level, but here's examples of funnel clouds. This was taken looking west on Highway 36, which is in northern Kansas, up towards Marysville, Kansas, in Marshall County a few years ago. And we had what we call a high precipitation supercell that was nearly wrapping this developing tornado fully in rain and making it almost impossible to see. This is viewing it directly from the east looking west. So if you were even a little bit further south, you would have been having a hard time seeing this one at all. So I'll look for the circulation beneath that to tell whether or not it's a tornado. Here is a sequence of events taken by a meteorologist of the Westmoreland tornado on April 30th of last year. You don't even necessarily see much of a lowering here, but we start to see the funnel develop here. And look at it in the second image right here. Is that a tornado? And the answer is yeah, it is. You can see some of the debris. We're probably 6 or 7 miles away. I don't know, somewhere in that ballpark. And so we were not real close, so it's not easy to see the debris, but there is some. We can see that cloud there. The other thing I'll mention here is based on our position. Do you see this little clear area here that's cutting into the base of the updraft? Well, that's one of those RFDs. We call it rear flank downdrafts. And doggone it, if you don't see this stuff time and again, and you did in the case of this tornado, it can be a red flag for the something to look for just before the tornado develops. And we see in this case what looked like a rope tornado turned out to be a strong tornado, even though it doesn't look wide, it doesn't look ominous, but it was a strong tornado in that case. Here's another classic case of a condensation funnel extending all the way to the ground. Here's one that's skinny. Does it mean that it's not as strong as this one? No. Or it's not as strong as this one? No. You can't necessarily tell how strong a tornado is necessarily by how wide it is. We've seen some wide tornadoes in Kansas that maybe did EF1, EF2 type damage, and smaller ones that hit stuff and did even stronger amounts of damage or higher degrees of damage to certain things. So can't always tell just by the appearance of a tornado. Question is, in this video that plays, is that a tornado? What do you think? Is it? And the answer is yeah, it is. Yep. Sierra says it is. You're right. You see the lowering, and it's anchored underneath that lowering. We've got circulation at the ground, and it's anchored. It follows that thing aloft. You see the rotation aloft in the base of the cloud. And the circulation at the ground is mirroring that motion. It stays underneath that. And indeed, that is a tornado. And the reason that we show this is that certainly around here sometimes we can get things that look like tornadoes, but they're not. They're tornado lookalikes. And this one's gotten a lot of attention here in the last several years because we've had high profile events that have featured things that look like a tornado, but they're not. And they are features that rotate along the leading edge of a gust front. And they're along the outflow associated with strong outflow winds. And they start to rotate and they look like tornadoes, but they're not. And this is an example of one of those. In this case, everything is moving right to left across your screen. And it's all associated with outflow. There's a shelf cloud moving over the top of us. You can't see it. But you see this little eddy right here, this little thing that's rotating. It looks like it could be a tornado, but it's not. It's actually what we call a gustnado. And you're saying, what the heck is that? It is. It's a gustnado. It's not attached to the base of the cloud. If you see something like this, immediately look upward and try to ask yourself, what's going on up here? Is this inflow and up? Is this the updraft region of the thunderstorm? Do I see organized persistent rotation about a vertical axis up here with a lowering? And that is that anchored to that feature down below? Or is it, in this case, something is sort of embedded in the more widespread outflow winds associated with the downdraft and outflow of a thunderstorm? It's called the gustnado. Thank you to Drone Lawrence, Kansas, who let us use this footage. They are looking at a cluster of thunderstorms that's producing 80-mile-an-hour winds across Topeka, Kansas. And Lawrence is just east of Topeka. And look at this. Look at this cloud feature here. This is a shelf cloud. So it represents the process of downdraft and outflow being dominant in this cluster of storms. And so we know back here there's a lot of rain and wind coming at us. You can actually see some dust. Looks like dust getting kicked up here. But I don't know if you caught that as the video was playing, but there's a little feature here. And I'm going to play it right here. And there it is. Right here, this thing got identified as a funnel cloud and a tornado. It's not. It's neither of those. It's some dust along the leading edge of the outflow wind that is being drawn up along the leading edge of the outflow. And sometimes as it gets drawn up along the leading edge of the gust front, it starts to rotate and it looks pretty scary. It looks like a tornado. But it's not. It's not a tornado. This is a case of blowing dust along the leading edge of the outflow. It's a gustnado, and sometimes people will see that and they'll think that's a tornado, and it's not. It's a gustnado, and a lot of scary looking clouds along the leading edge of these storms. Scud clouds and scary looking clouds are everywhere. You will see these more often than you will see legitimate funnels and tornadoes. The thing about Scud and SLCs, there's little or no vertical rotation about a vertical axis. You'll see some turbulent up and down motion, but they're really everywhere, and they don't tend to be organized. They can be underneath shelf clouds in the colder air. They can appear to touch the ground, especially if you've got high dew points and the cloud bases are very low. Um, they can, if they're in the right area associated with the inflow and updraft, can develop into a lowering. But watch them. The key here is look at this stuff. If you see scary looking clouds, watch it. Look at your radar app and ask yourself, what part of the thunderstorm am I looking at here? Is there inflow and updraft, or is this downdraft and outflow? This is a video that's an example of a scary looking cloud that is associated with a raggedy shelf cloud. A raggedy shelf cloud here. Rain is back here. So there's rain cooled air back behind it, and some of that is getting tugged back up along the leading edge of this. If you see something like this, watch it for a while and ask yourself, and look at the radar and say, all right, what's going on here? What part of the thunderstorm might this be? Is there organized persistent rotation here, or is this just upward motion? And oftentimes within a minute or two, you'll be able to tell immediately that, yeah, in fact, this is not a wall cloud or a funnel cloud. It's just a scary looking cloud hanging out, being tugged up into the updraft region or the leading edge of the outflow of a shelf. Here's another example of some scary looking clouds hanging down. Now, this is probably the updraft base of the thunderstorm, so it's very possible that these are being tugged up into a developing area that may organize into a lowering, a wall cloud. And so this might be an area to watch, a legitimate area to watch. But in this case, it's not a funnel. It's hard to tell. Not, if we really need video to be able to discern really what's going on in those cases. Here's another example of scary looking little fingers forming along the leading edge of a shelf cloud that forms. And you kind of see those little fingers develop right there. In real time, when these happen, they look scary because sometimes they actually can hang down and look like little funnels, and they're not. And even behind in the cold air, sometimes you'll see clouds hanging down and get misidentified as funnels, and they're not. They're just scud cloud, scary looking clouds. So there's a lot of stuff out there, a lot of tornado lookalikes. Watch out. If you see them, ask yourself, what part of the storm is this? Is this the right part of the storm? Inflow and updraft region. Do I see signs of organized persistent rotation? This case, this is actually a shelf cloud that's moving over the top of us. And because we can't see the horizon here in our perspective with respect to the wall or the shelf, it looks like a giant wall cloud or maybe a wedge tornado on the ground. It's not. It's a shelf that's moving over the top of us. Here's some rain shafts. Looks scary. Here's a smoke plume, refinery fire, or something going on here. The clouds are actually, or the smoke is a tracer in this case, and it's helpful. It shows you what the winds are doing. They're going into the updraft part of a storm here. So this is actually a legit area to watch for signs of maybe the development of a lowering. There's a little bit of a tail cloud or something hanging off the edge of here. So something to watch, but it's not a funnel in that case. The takeaway is this: there's more often than not, you're going to see things that look scary that are not tornadoes or not funnels. They can be gustnadoes, they can be scud clouds, they can be scary looking clouds hanging off of shelf clouds that are associated with downdraft and outflow along the leading edge of the cold pool of air that's formed by the downdraft and pushing away from the storm. Rain shafts, smoke plumes. This time of year in Kansas, we burn a lot of stuff, and so sometimes smoke plumes get ingested into the updraft of a thunderstorm as well. So that's the key point. Is if you're not sure what you're looking at, just take the extra couple of minutes to make sure that what you're looking at really is something that is important and not maybe a scary looking cloud as well. So real fast too, touching on radar, because radar is everywhere. And I think it should be an indispensable source of situational awareness information for you, no matter what your role is. Doesn't matter if you're a spotter for the county or you're just somebody that wants to stay aware on behalf of yourself or your family. Having radar is really a necessity these days. You have to have it. The way that radar works is inside this dome, there's a transmitter receiver that moves around. It starts sending out energy at about a half degree above the horizon, does a 360, listens for what's coming back to the radar, scattered back by things like rain and hail. And then it goes up a little bit, the next level, and does it again, next level, does it again, over and over again, until it does what we call a volume scan of the atmosphere. It goes up to 19 and a half degrees, and then it starts a new volume scan. Now, at the Weather Service, we have the ability to put it into different severe weather modes that will give us more frequent low-level half-degree looks, because what oftentimes in tornado situations, we want to know what's happening and how things are evolving at a half degree above the horizon. That gives us the lowest view above the ground of what's happening. That tends to be more important than what's happening at 20,000 feet when it comes to tornadoes. And so there's different things that we can do for getting that radar information. And then it paints a picture of colors and shapes for us. Based on what's out there, it scatters energy back to the radar. And in this case, it creates what we call the reflectivity product. This is what you're most commonly used to looking at on your radar apps or on television. This is the stuff in the storm. This is the rain or the hail. The colors represent the intensity of the rain or maybe the presence of hail. And then I said before, the reflectivity shapes can also tell us something about the processes in the thunderstorm. When you see this classic hook shape appearance, that represents the process of rotation. We know the storm is rotating. It has a rotating updraft out ahead of it. Does it guarantee that there's a tornado? No. It just tells us that there's rotation in this thunderstorm. We're dealing with a supercell. This is the reflectivity example from the big violent tornado that moved across Interstate 70 near the community of Chapman and east of Abilene, Kansas, back in 2016. This also took a jog to the southeast, and sometimes when we see storms do that, that's a red flag for them doing worse things, because it is a better orientation for ingesting more low-level spin, or it tends to give them an improved inflow air as well. And so I'll talk a little bit about that in a second. Here's this is about as classic as it's going to look. It's what's in the storm. Here's the hook echo shape. Where is the tornado? When you're dealing with classic hook echoes, the hook echo on reflectivity will tend to be near the tip of the hook, right here, right in this area. That's where they tend to be. That's the action area. The reflectivity, the colors represent maybe the presence of hail. You don't want to be in this area because that's where the hail is probably the worst. Forward flank downdraft, and then sometimes wrapped back around into the hook area of the thunderstorm. We also can see the velocity of things in the thunderstorm as well. The warmer colors indicate where winds are blowing away from the radar site. The cooler colors indicate where winds are moving towards the radar site. Where those come together oftentimes depicts an area of rotation. This is an example of that. This is an example of counterclockwise rotation that is likely surrounding what could be a tornado in this case right there, but that's an example of what we see on radar. When we put those two features together, the reflectivity signature that looks like this, a hook, with a velocity signature that looks like this, rotation. Oftentimes, we combine that with near storm environmental information like buoyancy and shear, along with spotter information, and that's what we really use for warning decision making. Radar information on the near storm environment, and then spotter information as well. This is an example of reflectivity and velocity data. Here is the radar reflectivity and velocity data example from Joplin, the EF5 tornado that occurred there and is one of the deadliest, I think maybe the deadliest tornado ever. And this is what it looked like. You see the classic hook shape. We see in this case what's called a debris signature, a debris ball. This is a very, very high reflectivity signature in the ball here, the tip of the hook. That represents debris, stuff that's being lofted into and rotated around the thunderstorm. And then we see here the very strong rotation adjacent to each other. Brighter colors nearby one another. When you combine that with a hook like this, that is bad. That's a bad, bad signature. Almost guarantees that there's a tornado on the ground. Not all the time, though, are you going to see a classic hook. Sometimes it looks like a kidney bean. Sometimes they look like a blob. This is the reflectivity signature of a high precipitation supercell that was producing a strong and violent tornado. Where is it? Well, you have to combine the reflectivity with a velocity signature. And then all of a sudden it jumps out at you. And it becomes apparent where that is. This is the storm relative velocity of the tornado that was otherwise embedded in rain and invisible to the eye. That moved across parts of Lawrence, Kansas into the western part of Kansas City back in May of 2019 as well. Now, these HP storms, they look different. Where is the tornado with respect to the reflectivity signature? It might be in the reflectivity notch a little bit further north. You don't have that hook. You just have a kidney bean-like appearance, or it's just completely wrapped in rain and just in the blob, and you can't see it at all. Here's an example of that, what I'm talking about. Here's the reflectivity signature. Where's the tornado? It's right here. It's in the blob. Where is it on velocity? Well, it's right here. It jumps out at you. Very, very bright colors next to each other. Inbounds here, outbounds here. And so we see the velocity signature of that feature as well. Here is the picture taken from Highway 59 looking north towards Lawrence, Kansas at the time. Can you see that tornado with a naked eye? No, you can't. It looks like a giant rain shaft right here. It's invisible. But one of the things that Doppler radar also now provides us the ability to do is to confirm that a tornado is indeed on the ground and lofting debris up into the atmosphere. Even if nobody can see it with their naked eye, Doppler radar has the ability now. It looks at the scatterers, if you want to call them that, the scatterers, and it tries to figure out what's the size and shape of the scatterers. And if they're all uniform, like raindrops or maybe even hailstones sometimes, they'll show up as sort of this maroon color. If they are all sorts of different shapes and sizes, the radar says, I don't know what the heck's going on. And it assigns a very low or near zero value here. And it shows up as a blue circle and otherwise a sea of maroon. And that we have learned, when you put that together with these other signatures, tells you there's a damaging tornado on the ground and it's lofting debris. They call it a tornado debris signature, tornado damage signature, and that can tell us that there is a tornado on the ground. This one had a debris signature up to about 16, maybe 20,000 feet during that event. We talk about it because our partners in the media talk about them. When there's something like this happening, it helps to convey risk and convey the fact that there is indeed something on the ground, and you need to do a faster job of actually personalizing the risk and doing something about it, taking shelter. And it helps to verify what's going on in that thunderstorm. So here's an example again of the idea that with reflectivity, you don't always get that classic hook shape. They can take on different looks depending on the environment they're in. They may look like blobs or kidney beans. They may have a hook, but they may also have lots of storm mergers. Mergers are very important sometimes for helping tornadoes to form. And sometimes they can mask the more obvious signatures of the hook that you might see. Now, there is a hook. You can see it in there subtly. And even when there's a merger, it's still there. But sometimes it makes it harder to distinguish what's going on. And here's some more examples of high precipitation supercells, kidney beans, with an inflow notch on the leading edge. Why do they have an inflow notch on the leading edge? The updraft can be it's where the updraft is stronger right here. It's more upright and it's stronger. And so you tend to have a little shape that looks like a concave area. Looks like a kidney bean. That might be something that you see with high precipitation supercells. I mentioned before, storm mergers are very important when it comes to supercells and tornado formation. And they're oftentimes easiest to see on reflectivity. And so we see here a lot of storm mergers going on. But one of the things you also see is how after the storm mergers occur, look at how this storm takes on a different storm motion. Oftentimes when we see a supercell thunderstorm that starts to march to the east-southeast, especially when all the other storms are moving east or northeast, that is a red flag that this storm has got something different about it. And it might be greater low-level spin, It's able to ingest more spin in the low levels, or it just has stronger inflow because it is taking a jog to the south, and winds in the inflow region are from the south. And so it's these storms that deviate from, they call them deviant movers, that we really look for the nasty ones that are up to no good and may produce worse things like bigger hail or tornadoes where other storms don't. There's a lot of in this animation. There's a lot of things going on all at once. But the point that I want to make for you is watch for the storms. Look at this big one that takes over, and it starts to move east southeast, where a lot of the other storms are moving northeast or even just due north. And so watch for these, the ones that take over and have a deviant motion towards the east or east southeast, and even the other one up here, this one right here, was doing something similar. So those are the ones you want to watch. Storms that are out ahead of a line and take on that sort of emotion, red flags. You want to really watch those storms for the development of a tornado as well. Just sort of a review with reflectivity signature. Tornado can be near the tip of the hook with high precipitation supercells, maybe near the notch on the front side. Lines of storms, I don't talk about this very much because, quite honestly, you're not going to see squall line tornadoes. They tend to be very small, embedded in rain, and they don't last very long. They tend to not last very long, so they're more difficult to see. But if you're curious, they tend to form near the apex of the bow or just north of the apex of the bow. And that's where you tend to see their very small scale transient signatures on radar, usually with the storm relative velocity. We'll see those as well, but that's where you tend to see them on the reflectivity signature. Reporting severe weather, time, when did it occur, location, where are you? I'm in Topeka, and I'm looking to my north, and I would estimate 5 miles north, I see a rotating wall cloud. The difference between where you are, the direction you're looking, and the distance, if you can estimate it, that's very important information. Who are you, and what are you reporting? The thresholds for severe thunderstorms: 58-mile-an-hour winds or greater, quarter size hail or larger, any sort of wind damage as well, funnel clouds. Flooding is also information we want to know about, so we can get that information out to as many people as we can for situational awareness purposes as well. People ask, how do you estimate a wind speed of about 60 miles an hour? And it can be, if you got trees around, and it can be a tree branch about the size of your wrist. And if it breaks, that can be an approximation for a 60-mile-an-hour wind as well. Safety, awareness, communication, escape routes, safety zones. This is all very, very important information to remember as well. Safety tips for lightning. If you're close enough to hearing the sound of thunder, you are close enough to being hit. The old rule of thumb is you hear or you see the flash, count the number of seconds between the flash and the bang and divide by 5. It gives you a general idea in miles of how distant or how far away that lightning strike is. The takeaway is this: that lightning tends to be closer than you think. If you hear thunder, get into a building, if you can, a house, structure, enclosed structure. If you can't, just go into your car, a hardtop vehicle, keep your hands inside, roll up the windows. That is the fastest, easiest way to keep yourself safe from lightning, and stay inside until the storm has passed. Flooding, when it comes to flooding, don't do this. Just don't do this. We lose more people every year from thunderstorm-related flooding in Kansas and across the country. It's when people do things like this. And so we just ask people, when you come to a flooded road, turn around, don't drown. Doesn't take more than a couple of feet of water to make a car buoyant. And if there's a current, you're going to go with it, and you're going to start floating like this guy right here. And then that's when the emergency responders need to get out and rescue you. This guy got caught up in the trees, and the EMS folks had to get out there in a boat to take him out of his pickup. So not something you want to do. You're going to destroy your car and put your life at risk. Doesn't take much water to make a car buoyant, and even just if you're walking, it doesn't take that much water to knock you off your feet as well. Tornadoes and cars. Tornadoes versus cars. Not good. This is a photo that was taken of the remains of some cars that were in the parking lot of the YMCA in Andover, Kansas, when a strong tornado hit a couple of years ago. Now, Andover, if you don't know, is a community that's just northeast of Wichita, Kansas. Was hit by a big tornado back in 1991, and they had another big tornado, strong tornado, back in 2022. Everybody that was at the YMCA sheltered in the locker rooms, they did what they needed to do according to their plan, and they were okay. Nobody was in these cars, and it's a good thing because you could see here you would not have fared well if you were. Some of these things, seeking shelter in a sturdy area is what you want to do. You want to get into a shelter if at all possible. You don't want to stay in your car and ride it out in a tornado because that's extremely dangerous, especially if you're up against a strong or violent tornado. It's terribly dangerous. These are absolute last resort recommendations, or not even recommendations. Recommendation would be don't be in a car in a situation like that. There's lots of information before you get to that point that are available with your radar app, with the watch that was issued maybe 3 hours before the storms got into your area, that can give you the information so that you change your behavior a little bit before the storms arrive, so that you're not as vulnerable as you might otherwise be. Otherwise, these are absolute last resort. Leaving your car to get to a ditch. This is kind of like somebody telling me I can punch a shark in the snout if I'm in the ocean. I guess I can do that, but I don't want to. I don't want to be in that situation to have to do that to survive. And it's the same in this case. I don't want to have to jump out of my car and into a ditch. I want to do everything possible before that gets to that point to avoid that situation, if at all possible. How to submit reports: social media, X, formerly known as Twitter, is probably the fastest way. We're on there. You can tag us by using this at NWS Topeka or that hashtag there. We're still using hashtags for following feeds of weather information. That's still a good way. I think that's the last slide. That is the last slide. So I appreciate everybody hanging out with us tonight. Whether you're from Kansas or not, it doesn't matter. Wherever you're from, stay safe. Severe weather season. There's plenty of tools in this day and age to keep yourself aware and keep yourself safe before the storms arrive. So again, thank you for joining us, and stay safe, everybody. I will keep this open for a little while longer. If you have any other questions, one of our meteorologists will do his best to answer them. Otherwise, yeah, thanks a lot for hanging out.